going to be teaching you how to solve a triple integral as stated on the screen, 3x to the third plus xy squared dv, and specifically I want to talk about setting the bounds. So since we're in the first octant, we know that our theta goes all the way up to pi over 2 and no further because the first octant of a circle goes from 0 to pi over 2. This will set our theta bound. And this paraboloid that we have here, given in the specifications, of course, this is given for the problem, 16 minus x squared minus y squared gets us 16 equals x squared plus y squared. And since z is equal to r squared, we know that r equals 4 at its maximum, which means that we can set our r bound to 0, less than or equal to r, less than or equal to 4. This is just based on how paraboloids work and how first octants work. So that means that we can go ahead and set up our integral in notation as 0 to 16 minus x squared plus y squared. But wait, we have to convert over to polar coordinates, which means that 16 minus x squared minus y squared is equal to z, and z is equal to r squared, which means that we're going to do a little bit of algebra magic here and go back to using our 16 equals r squared equation from earlier. This will allow us to convert into polar coordinates the initial 16 minus x squared minus y squared. We'll be able to convert it to be 16 minus r squared equals z squared. Equals z, I mean. So that's also given if you were to evaluate x squared plus y squared and subtract it from 16, x squared plus y squared is equal to r squared. There's multiple ways you could have found this answer, but we're going to go ahead and stick with that 16 minus r squared equals z. That's the maximum value that our z can have, and our minimum value is our 0. So our z top is 16 minus r squared, and 0 is our z bottom. This is just because we're going to set it up now with 0 to pi over 2, 0 to 4, and 0 to 16 minus r squared because this is our z integral, which gets us into our rest of our integral. And the reason that we can set it up this way is because you can technically do this in any order, and I'm going to actually go ahead and use blue now, but you can do this in any order, but it's generally, except for the z, you're going to want to leave the z as your innermost integral to evaluate. You're going to want to evaluate that one first. Now, when we're converting our function also has to go from x squared plus y squared into polar coordinates, or theta, and that's going to be not much trickier than converting that 16 minus x squared minus y squared into polar coordinates. So x squared plus y squared is equal to r squared, and I'm going to go ahead and actually do this in pink. So you can, again, take this in any order except for the z top and z bottom. Those need to be on the inside because if you don't integrate the z first, then you end up with a variable in your final answer, and the whole point of integrating the volume of a solid, that's what this is, we're integrating the volume of a solid, an irregular solid, the point is to get a scalar. So we don't want any variables in our final equation, which is why we have to integrate that variable first to get a number. So our equation right now as it stands is 3x times x squared plus y squared. X squared plus y squared is r squared, so it's 3x times r squared is going to be our final equation in terms of polar coordinates, and that's just pulling off of that top one right there. And it's really important to remember to convert your function into polar coordinates as well as your bounds. So I always used to forget to integrate my bounds using r coordinates and theta coordinates, or polar coordinates. So I do them first now, but you can do them second. It doesn't matter a ton as long as you find them eventually. Now we have 3x r squared, and that's just because, again, I removed that x from the x cubed plus xy squared, and I put it on the outside. So it's 3x r cubed dz dr d theta. And that order actually is important for dz to go first. Dr and d theta can be integrated any other way you want. We're going to pull the r out of our x equals r cosine theta and plug it back into our x. So we actually end up with 3 cosine theta r to the 4th dz dr d theta, and that's how you get your final equation. Of course, you can always go back and clean this up a little bit, but once you have the bounds, you'll be able to do your integration fairly easily. This works out just as any normal integration problem for singular integrals, and you're going to want to take this one at a time. A lot of people will tend to try and keep using the tricks that we learned for multiplication, but generally speaking, you're not going to want to do that here because we have that variable in our dz. We're going to need to plug our dz into our dr. But the dr and the d theta can be multiplied against each other if you integrate with cosine first. And this, by the way, all this on screen is just me kind of cleaning up the work that I did previously.